Now in this video we're going to take a look at determining the moment of inertia for a solid disk. Now once again, this is not an unknown geometry, but we are going to show and demonstrate the calculus way of determining the moment of inertia. So we automatically expect that we should get I for the disk is equal to 1/2 mr squared. Now this technique is going to be just slightly different from the other, only in that whenever we solve this problem, instead of using lambda, which is what we typically use for mass density, we're actually going to be using sigma this time. So let's start by setting up the problem using our definition. I is equal to the integral of r squared dm. And remember before that the key step is taking a dm and turning it into a dl, a dA, or even a dV for volume. So we do that by writing sigma is equal to m/a, and in the limit we end up with dm dA. Now for this particular problem, our axis of rotation, as always, is going to be through the center of mass. So it's going to be right here. And our limits of integration are going to go from inside to outside. So from the center to the outer edge. That's going to be from 0 to capital R. Because remember that a capital R indicates that we're looking at a constant of a problem, and lowercase r indicates that we're looking at a variable within the problem. Okay, so basically what we get is this: I is equal to the integral from 0 to r of r squared. Now dm is going to become sigma dA. dA still is not a known value. We need to get this down to r, where we want to integrate it with respect to r. So the dA is going to have to be transformed into something with a dr. So dA is really nothing more than a differential area, or you can think of it as taking the derivative of the area of a circle. And so we get dA is equal to 2 pi r dr. Now you might be asking yourself, where does that come from? So conceptually, what we're looking at is this ring here. Now I've got it drawn very thick so that it's easy, the black ring, so that it's easy to see what my label and my diagram is. But in reality, this is an infinitely thin ring with only an infinitely small thickness. So I can draw that, and basically what we're going to do is we're going to cut that and lay it out flat. So we go from a circular ring to something that looks like this if we lay it out flat. And so it would have a thickness, if we drew this with a thickness, it would have a thickness of dr, and the length of that would just be 2 pi r, or the circumference of a circle. So 2 pi r times dr gives us dA. So I is equal to the integral of r squared times sigma, which is mass per area. So we'll just write that now, m/a. And dA becomes 2 pi r times dr, and this goes from 0 to capital R. All right, so now we're just going to pull out all of the constants, and so we get I is equal to 2 pi m/a times the integral from 0 to r of r cubed dr. And now that's an integral that you should easily be able to do. So we get I is equal to 2 pi m over, now area is pi r squared, so that's going to be a capital R, because this area is the area that's a constant of the problem, which is the entire circle itself. So this becomes pi capital R squared. And then the integral of r cubed becomes 1/4 r to the fourth. And then we evaluate this from 0 to capital R. Okay, so let's do a little more simplifying, and we get I is equal to, so see, we can cancel out pi, and that's all we can cancel at this point. Or, well, I mean, I guess we could see that this 2 and this 4, they reduce down to 1/2. So you should be able to see that we're starting to get close to that 1/2 mr squared, because what we have is 1/2 m over capital R squared times r to the fourth, evaluated from 0 to capital R. And it should be obvious that we're going to end up with 1/2 m over r times, squared, m over r squared times capital R to the fourth. And so this r squared cancels with 2 of those r's, leaving us with I is equal to 1/2 m r squared. Okay, and that's what we were setting out to show. So this is for doing a solid disk. Now, what I want you to do for a moment, pause the video, take a moment, and try to determine the moment of inertia for a thick ring. Now remember that a thick ring is one where it's hollow in the middle, and this outside diameter is fairly large. So take a moment now and try that on your own. Okay, so let's take a look at how you would go about doing this. You should have at least been able to just set it up, if nothing else. And the setup actually is the same setup as what we do for the solid disk, because we're still basically dealing with a disk. And just like we did with the long thin rod, so we can also do with the disk. And what I mean by that is that when you've gone through and you're setting up your calculus, the only thing that's really changing is our limits of integration. So once we get to this step right here, once we get to this step, all we have to do is change our limits of integration. In fact, I'm going to take it down to this step. I think that one's a little easier to work with. So you should get I is equal to 2 pi m over this area here. It still represents the same thing. It's not going to change. That would be the total area of your disk. So basically, what's the area of the circle minus the donut hole? And so to get that area, you would have pi times r outer squared minus r inner squared. Okay, so that's the setup part of it. Now this is all of our constants of the problem. So then we got to finish by doing the integral piece. Now our limits of integration would go from, if we look at this particular problem, let me do it like this. We're gonna go from, we're gonna say that this here is our thick ring. Okay, we're gonna ignore all that stuff in the middle. And so basically we have R inner, and then we have R outer. Okay, so we're just looking at this part of the ring. And that's a constant within the problem. Okay, so we have the integral now going from R inner to R outer of r cubed dr. So this is a little r, that's going to be cubed times dr. So now I is equal to 2m, remember that these pi's here will cancel, 2m over r outer squared minus r inner squared And then the integral of r cubed is still 1/4 r to the fourth, and then we have to evaluate that from r inner to r outer. And the rest of this is really just algebra. Okay, so what we end up with is I is equal to, remember that this 2 and this 4 reduce down to 1/2, so we get m over, well, let's do it like this, 1/2 times m over r outer squared minus r inner squared. And then this r to the fourth, it's going to become r to the fourth outer squared, r outer to the fourth minus r inner to the fourth. And at this point, you're technically finished. Now, if you look this up in a table somewhere, what you get is I is equal to, for the thick ring now, I is equal to 1/2 m times r outer squared plus r inner squared. And you say, okay, this does not look like that. And certainly you can't just reduce this down and try to cancel out the r outers and the r inners so that you get r squared and r squared, because that's a minus sign, not a plus sign. So the real question now is, how do we do that? But before I address that, I just want to point out that this is a valid way of solving it. So even if you couldn't finish the algebra on this version of it, it still is going to work okay. So from here on out, it's just a matter of putting it in perhaps a more usable form because it's simplified. But here's the test. If we make r inner go to 0, then what we have is a solid disk. And a solid disk we know is 1/2 m r squared, where the r really is the outer radius of the disk. And so if this term goes to 0 and this term goes to 0, then we get r to the fourth minus r squared. R to the fourth divided by r squared. So this would cancel with 2 of those, and we end up with 1/2 mr squared. So this is a valid representation, it's just not in its simplest form. But let's go ahead and discuss now how you would go about putting this thing into its simplest form. And basically the way you do that is you have to focus on the r's. And so we get this expression here, r outer to the fourth minus r inner to the fourth over r outer squared minus r inner squared. So the way we take care of all of this is we got to focus on what's happening in the numerator here. For this, we're going to use a binomial expansion, and basically it's difference of squares. Okay, so we're looking at difference of squares, a squared minus b squared. That's going to be the same thing as a minus b, a plus b. All right, so that's basically what we're doing here. And when we do that, we get r outer squared minus r inner squared times r outer squared plus r inner squared. And now if we were to place that in the numerator, so we have I is equal to 1/2 m times r outer squared minus r inner squared times r outer squared plus r inner squared. And then we divide that by r outer squared minus r inner squared. Then what we end up with is the r outer squared minus r inner squared cancel. So this term and this term cancel, and that just leaves us with I is equal to 1/2 m times r outer squared plus r inner squared. Okay, so there was really a lot to bite off whenever we did this second one, but I just wanted you to see that, just like before, that the setup itself fundamentally is the same thing. Once you get that integral done, all you have to really do is change your limits of integration.